Okay. Thanks, Josh, and thanks to everybody at Neo4j and Goldcast for helping me out get through the technology of this. My talk today is really a combination of three different technologies. We're talking about graph databases, we're talking about structural trees, database type trees, and data analytics to reconstruct an ancient river system. And for people that are just coming into this talk, what I would, suspect is you're wondering, why would you ever want to reconstruct an ancient river system? And the answers are kind of twofold. The first is by reconstructing it using a combination of these technologies, you can get an understanding and greater knowledge of the climate and the different kinds of geology that were going on millions of years ago. And so certainly you'd gain from the knowledge. But the second goes back to my very first career. I'm on my third career now, but my very first career was as an oil exploration geologist. And one of the things that came across on that was that ancient river systems can sometimes be the host of significant oil and gas deposits. Now, we're going to look at this little 5-step overview of the talk. And first, graph trees, you may or may not be familiar with this. So we're going to talk about that and talk about some of the natural applications of graph trees. Then we're going to ask, can a river be modeled as a tree structure? That's a key thing if we're going to be able to, use the data analytics on it. And the example of this will be from an area in Colorado where the Sandstone of Cretaceous age is very oil productive, but there's also a lot of data, so we can use data analytics on it. And then the question becomes, how would we model it? The very famous and the classic Seven Bridges problem, the Seven Bridges of Königsberg, was a similar kind of a situation. And originally the land in Königsberg became nodes, and the bridges over the rivers became links. Now we're going to reverse those. And then we're going to get into the data analytics, modeling the river, which PageRank, and why PageRank was selected when there's so many different kinds of data algorithms you can use. And then at the final part of the talk, we're going to compare what PageRank told us with the published data and answer, does it match? Now, starting off, as I promised, we're going to look at what trees are. In computer science and graphs, trees are very, very often used. And so we'll ask what, from a graph standpoint, is a tree structure. And these are three examples of tree structures. In order to fit this category, it has to be hierarchical. And there you can see this particular one on the right definitely is hierarchical. There are no cycles, aka acyclic, and there's only one path that exists between any two nodes. And, it's obvious that the one on the right is a tree structure, but the next two next to it are also tree structures, because this one on the far left that goes up and down is a line, but it still fits the definition. It's a hierarchical data structure. There are no cycles, and only one path exists between any two nodes. Now, this is true, so we can start broadening our mental concept of what a tree structure is. But I want you to take a close look at this one in the middle, because this particular tree structure is something that we're going to see later in the talk. And notice that basically what you have is a series of nodes and links that come to a center point, and it looks like it's almost mirrored coming on down from there. And one last comment on tree structures here. They're one of the most popular data structures in graph databases, and I'm paraphrasing an article by the two people down at the listed at the bottom of the slide. Now, of course, in computer science, binary search trees are very, very important, particularly in the database world. And in this particular example, The root has a value of 45. And if we were to put a second number into this tree, it has the rule that larger numbers branch to the right, and smaller numbers branch to the left. So what happens is this 45 comes in, and if you have a 15, then what ends up happening is you branch this way. But if you had a 45 higher than 45, it would branch this way. And basically, you're building a tree structure. And like I said before, this is very, very common, particularly in databases. And of course, you could look at this as a graph at the same time. Now, one of the things that fascinated me in my third career, first there was geology, then it went into computer science, and then it went into, basically graph databases. In my third career, I was working for a biotech firm, and they were building graph databases, Neo4j graph databases, as a matter of fact. And one of the reasons that they were building these is because there are so many parts of biology that actually show a tree structure that actually can be modeled with a graph database. And I just picked out one, for example, here to show you that, for example, if you've scraped your knee and you've got, a blood coming out of it, you've got a damaged surface, and then the body will go through a series of steps and a series of compounds, a pathway, if you will, that to be able to build the clotting material and stop the blood flow. And here you can see it all the way down from this to this to this to this. And then, of course, part of it goes to here. And just like if we were looking at rivers or tree structures of other kinds, there's a second path of flow that's coming in here. This is for a major blood trauma, major body trauma. And there it also builds a series of sequences. Then they come together just like a river coming together or a tree branching. And then you get the final chemicals, which actually will form the blood clots. So that's another example. But like I said, in my first career, I was an oil geologist, and rivers were something that was very important because they generally are very sandstone rich, and they can form some great oil deposits. But the question becomes for us, is a river system something that we can model as a tree structure and model in a graph database? So let's look at this. This is a picture of the Mississippi River. And of course, the Mississippi River is the largest of all the rivers in the United States, going all the way from Ohio on up into Idaho and Montana. And if we look at it, we see that river systems fit the definition of a tree structure. Up here in Idaho and Montana, you have the smallest tributaries that are coming together to form a larger stream, and then the multiple streams come together to form the Missouri River, and that comes into the Mississippi. So yes, they're hierarchical. Yes, they have no cycles, and they also fit the definition that there's only one path between the different nodes. Now, everybody that's really looked into graphs has certainly come across Leonhard Euler. He was the Swiss mathematician that was the inventor of graph theory. He was famous for many kinds of mathematical discoveries, but of course, here today, we're looking at one of the best known, which is graph theory. And he developed graph theory to solve a problem. The people of Königsberg, which was in Prussia at the time, now I believe it's in part of Poland, but somewhere around the Eastern Europe area. Anyhow, Königsberg had 7 bridges which linked the different parts of the town. And what ended up happening is they put out a challenge a challenge for mathematicians to be able to solve. And this challenge was, is it possible for a person to cross each of the bridges, each of the 7 bridges, and complete that, but at the same time not having to cross the same bridge twice? And Leonard Euler invented graph theory, which, among other things, was something that allowed the solution of this problem. And what you're looking at right now, this is, of course, the city, and the bridges are in green. But what ends up happening is we need to convert this to a graph. And the very first stage of that was to take and use the map with the bridges, with the islands and the land areas, and then convert that to something that was more graph-like. And the middle diagram of this shows only the bridges, yellow, and then the land, green. So we're getting there, but we have to go one more step further. We have to take what we're looking at in diagram 2 and convert it to a graph. And that became the picture that you see in figure 3. The land areas, the islands, and the land areas here in green became nodes, and the bridges became links all the way across. And you'd see that, for example, this one land area has a link to this area, and then it has 2 additional links to 2 more land areas. And so to solve the bridges of Königsberg, Leonard Euler came up with graph theory. Now, this is great, and this worked, and the question becomes, given what the title of this talk is, how are you going to model a river system? And the very first question you have to ask is, does it fit the tree structure that we've been talking about? And here's a diagram of an idealized river system in the United States, or it could be any place in the world. And we have to look at this and see, does it fit the idea of a tree structure? Well, let's look at the mountains up here. We could look at this as Rocky Mountains, where I happen to live, and you have smaller creeks that are coming down from the mountains and joining up to form larger streams, and then they come out onto the Great Plains. So we could look at this as the Great Plains, where the different rivers come together. You could even look at this, if we were looking at some of the rivers that we've got here, we could look at this as the Missouri River, this one could be the Platte, and this one the Arkansas, and then what we're coming down to is the Mississippi. Now, keeping in mind that second diagram of a network, of a tree structure, we're starting to look like this, because what happens is you've got these smaller links that are coming down. They join together, but then remembering that the second part of the tree structure, what you have after the Mississippi River flows through the heartland of America, it goes to the delta, the Gulf of Mexico delta, and there it reverses. Because the river slows down, what happens is the water flow diffuses, and it acts like a network. And it goes from the largest, the Mississippi River, into a series of forks, like you'd see in the Bird's Foot Delta in Louisiana. And it forks back out. But by doing this, it doesn't break the rules of a tree structure. So it looks like rivers do fit tree structures. But now we've got the next thing we have to solve, which is, okay, this is a tree structure, but how would we model it in a graph? And we'll look at the next slide and we'll see. Okay, you remember back when we were just looking at the 7 bridges of Königsberg, that the land was the nodes. Well, I reversed that for this. I made the river junctions nodes. And then, of course, the rivers flow from up above in the mountains all the way down to the Gulf of Mexico. So you've got knowledge of the flow directions. So in order to model the J sandstone channels, those rivers, what I did is I digitized. Let's look at this. Here we go. The very first step in the river channel modeling was to build a graph database model of the channels using published data from oil and gas wells and dry holes. The oil and gas wells presumably were coming, and we could certainly get down and confirm this, were coming from the J sandstone. And there was a lot of data because that particular area of northeast Colorado is very oil productive. And of course, dry holes where they missed the sandstone still gave us data because there might be some sands that were connected into the system, but still not oil productive. So the very first step is build the graph database model. Then we had to evaluate if the graph accurately represented the channel network. You know, if we were going to use data analytics on it, we had to know that our mathematical model, the graph, was close to what we were seeing from the published data. And then we applied PageRank data and analytics to the graph model data. Now I'm going to go into why I selected PageRank in some of the later slides, but you might get kind of an idea of why, of all the different data analytics models and algorithms that we could have produced, that we could have used to model this data, PageRank was the one I chose. And then, of course, once we've modeled it with PageRank, we're going to look and see if the various channel values matched the PageRank values. So here's the very first step. We've got to get the data and build the graph. One of my professors, Robert Weimer at the School of Mines, and one of his grad students, Steve Sonnenberg, did a very detailed study of the J sandstone channels. Oop, we got to go back one. Okay, we need to go back to, there we go, of the J sandstone channels in the area of northeastern Colorado, and then the adjacent areas of Wyoming and Nebraska. And what ended up happening from these maps, they mapped them, and what ended up happening is they provided what I was looking for, what I needed to do the modeling. Wherever I had a junction, a river junction, was where a node went. So there'd be one here, one here, one here, etc. And these two people actually went and also interpreted the river flow networks. So I knew which direction in a directed graph that the particular nodes linked up in. And you can see from these arrows coming through that the predominant flow directions in the J sandstone channels were primarily, I mean, there's a little bit that goes to the southwest, but most of it goes to the southeast. And for scale, right down here at the bottom, you'll see what 50 miles works out to be. So you get kind of a feeling for how large an area we're looking at. You know, something that's perhaps 150 miles wide and then perhaps 300 miles high. And since this is, of course, a graph talk, we're going to talk about how we represented the nodes and the relationships in the graph database. What we've got, like I showed up above, where there were junctions of two rivers, then we would put a node there. And then we knew from not only from the arrows that he put in, but also the fact that the river channels were getting bigger as you went further and further downstream towards the deltaic outlet, that we have. And let's just look at a couple of these graph nodes. What you see is two numbers in there. And the first one from my digitizer was the X value, and the second one from the digitizer was the Y value. And what I ended up doing, I had all of these data values in a Neo4j graph database. And so what I did is I took and exported it in GraphML format, which is one of the several formats that Neo4j provides. And then I incorporated that, uploaded that into another graph database. Well, I should say a graph visualization software called Gephi. And that one was the one that gave me the ability to plot these wells in X and Y form. And so this is what I came out with. The diagram on the left is the same one we were looking at 2 slides ago. So what you've got is the basic channels, and I took the location right here, for example, or right here where the rivers come together. That corresponds to that node. And then up here, just above that, is another node where the junction comes in. And then you see here, where these 2 rivers come together, there's a junction. And then you work your way on down. And by looking at it, you could say, that looks like a pretty good representation of what's happening. Now, of course, the actual river flow directions, I took from this published information, and also from knowledge that when rivers come together, smaller ones beget larger ones. So I know, for example, that the flow direction right here is from there to there, and the same thing here. What you look at is flow direction, because as you move on down, the river system gets much larger. And if you compare that to the J sandstone channels, you'll see that exactly models it. So from the first standpoint, did I have a good representation of the actual data, digitized from the published information? And so, yeah, I'd say I did. Now, we're going to talk about the data analytics part of it. We've talked about tree structures. We've talked about graph databases, holding it, holding the data, and also, like I said, the plotting software in Gephi. And we're going to say, what is the PageRank algorithm, and why did I apply it in this particular case? Now, as I think almost everybody knows, the founders of Google, when they first founded the company in the late 1990s, what they did was they faced a problem about search results. In fact, if you do a Google search today, you don't even have to get into the really obscure searches, because you're still likely to come back with thousands of results, maybe tens of thousands, depending. And Google faced the problem that if they were going to display these results, they didn't want their users to be able to take and have to page through 30,000 results to find which ones were the really good ones. So they developed the PageRank algorithm. And the idea being that they would take the most popular and likely most relevant to your search results and display these results in descending order. The most popular links appeared at first, the top of the list. On a first blush look at how PageRank works, what you'll see is that each one of the search results is ranked by the number of incoming links, the number of pages that point to it, with the idea being that if lots of people are pointing to a particular search result, that it must be important. And the higher numbers of links produce higher vote counts. Now, this is great, but unfortunately, the real world is more complicated than this. You can't just simply take the incoming links as the be-all, end-all of your PageRank value. And we'll see that in the next slide. Because sometimes a search node can have a complex network of links. And so the vote counts for PageRank determinations include not only the incoming link counts, but formulas to derive the PageRank value of each node. This is an example. And I took this from Wikipedia, and because it shows a number of things visually for PageRank, the very first thing you'll notice is the different sizes of the circles that are on there. Each one of the circles represents a website, or a link, I should say. And so what ends up happening is that the larger the circle means it has more overall input from either the direct links or the side links that are coming into it. Let's take, for example, the red circle. Size means that it's got the highest PageRank value. So, for example, this red PageRank is fed by the yellow PageRank, which is fed by these 5 purple ones, but it's also fed by these 2 green ones. And what makes it a little complicated here is that you've got, it's not a straight line. What comes to the yellow, that's a straight line from the purple, but then it goes off to the green, and then there's a second link that comes back to the red, whereas at the same time, you've got a link from the yellow. So it's a little more complicated, but like I say, at first glance, you could look at it in terms of incoming link counts. Now, let's take a look at what would happen. Why would I use PageRank to map channel sands? Okay, this is a key question. I'm sure a lot of you guys have already figured this out. But essentially, the reason I chose PageRank to model these channel sands is because PageRank basically tracks a numeric value for information flow, links, information flow. So that what happens is higher up in the hierarchy, what you've got is links coming on down, and then they join together. And as you can see from the size, the more links and the more complexity, the larger the size. Well, we were looking at information flow, but I thought to myself, you know, this is really analogous to water flow. What you've got, like to pick these up here, you've got small tributaries, and the water flows down them. And then when the tributaries join together, there's a greater water flow that comes to the next tributary. And then as succeeding numbers of tributaries go together and just come together, then you get greater and greater water flows. And it occurred to me that this was analogous to links, that you might have, you know, some page that's way out there on the internet, and it's got one link going from it and no links going into it, i.e., it's just very much like these very small tributaries. And as more and more tributaries link together, there's more and more water flow. And as more and more PageRank values are computed together, there's more and more PageRank values, higher, if you will, information flow. So that's why I chose PageRank. And there it is right there. It's a measure of link flow, and it's appropriate algorithm to apply to river channel flows. Okay, now this is the chance for us really to go into it and say, okay, that was a nice, you know, that was a nice bit of conjecture, but does it really hold water? Well, let's compare it. I exported the values, the locations into Gephi, and Gephi took and did the data analytics of the PageRank values. And then on top of that, what Gephi did is a really nice job of color coding it. And as you can see on the screen on the right, what you have, the lowest PageRank values, i.e. the smallest water flow, are light blue, and then the highest ones are in the dark color, almost black. And now let's kind of compare this to what we've got in the original data. Here we've got a major river channel that has got a series of tributaries coming into it, you know, and then for example, this node here would be placed right about here, and then this node here would be down here, this node here, etc., and then going on down. And what you see is that the mapped value of the sandstone channels directly corresponds to the PageRank values. So that confirmed that PageRank was a good algorithm to model this. And of course, you know, given my first career in the oil business, it was the kind of thing that made me, you know, say, well, gee, if it has a higher PageRank value, maybe it's something with a larger river channel, and maybe it's a place to go explore. So this was the first comparison, okay? And then let's look at the second thing. I mean, we've got these river channels, but at the same time, you know, width is one thing, and we're just looking at channel width. But another value, is that evident? I'll finish up now. There we go. Okay, thank you. Thank you. I'm sorry I went over. The last slide here is to look at porosity values, which are here, and then coming on down, and the porosity values also correspond to the high PageRank values. That's it. Thank you for letting me go a little over.